continue with the noise theory and how to measure noise in a two-port device. So a two-port device is a device which has one input port exclusively and one output port for taking out the output. So we are very much concerned about how to measure noise in a two-port network. So any device, any ideal device, we assume it has zero noise. The practical device, practical two-port device will have some amount of noise because of resistors you are going to use, because of the device parameters what you have, because of fabrication methodology. So all these things will contribute to the noise of a two-port device. This two-port device can be a diode, it can be an amplifier, it can be a mobile phone, it can be any application which is going to have two ports. Okay. So how to measure the noise? So for measuring the noise parameters of this two-port device, I'm going to excite the device with the current or voltage. So either I can use a current source parallel to admittance, or I can use a voltage source for uh, for the device. So this IS and YS are going to be the source input source signal, and EN is going to be my noise. EN and IN is going to be my noise voltage or noise current. So we usually measure the noise performance of system by one parameter called as noise factor. The noise factor is going to be denoted by capital F, and we are going to see what is the relation between F and the parameter shown in the diagram. So I am going to consider a noisy device which is driven at the input side. I'm going to have this noise. So it is going to have an admittance of Y, and it is going to have an equivalent shunt noise current. So I am going to excite the device with a noise voltage En, and it is going to have a noise current In apart from the input signal Is parallel to Is. See, whenever you are going to use a current source, you'll be using parallel to a conductance. Whenever you are going to use a voltage source, you'll be using series with the resistance. So here I'm going to drive the two-port network with the current source. And I am also going to excite the same network with noise voltage and noise current. Again, you see it is En bar and In bar. So it is going to be RMS value or the average value of noise voltage or the average value of noise current. So if we are connected only with the overall input output behavior, we have to track all the noise sources. So any device you take, if you want to analyze the noise performance, you have to consider all the possible noise sources. You have to use superposition theorem, and you cannot find the total noise power in a single step. So you have to consider one noise source at a time, find the effect of that noise source, that is power P1, second source, power P2, third source, power P3. Total noise power equal to P1 plus P2 plus P3. That is what is usually done in all the circuit theory problems. Right? The same way see here, the net effect of all the sources. Finally, I can replace everything by a single noise voltage and a single noise current. So finally, if we simplify a network using Thevenin's theorem or Norton's theorem, we'll have a single voltage source series with a resistance, or I have a single current source parallel with a resistance. So finally, if you consider all the noise parameters in a two-port network, I can simplify them to a single noise voltage or single noise current, which will represent the sum of all the noise currents inside the device, or the sum of all noise voltages inside the device. Okay, that is what is done here. We cannot compute them individually. So we have to compute them for each noise, add them up, and you will get the total noise voltage or total noise current.